myself. Okay, we're ready to get started. Anybody have any questions on anything? Okay, then I'm going to go ahead and open this up. Hopefully I've got the right PowerPoints up. There we are. Okay, everybody should see the PowerPoint that says the superior and inferior colliculi showing up there. That's about where we stopped last time, at least according to YouTube. So the corpora quadrigemina is a good place to start over again. Corpora quadrigemina is an important reflex center in our brain. It's what allows us to turn our heads when we notice motion. The retina in our eye is composed of photoreceptors of cones for color vision and visual acuity, and rods for shades of gray and night vision. And they also tend to line the edge of the retina, so they're really good at picking up motion. You know what we call our peripheral vision, the corner of our eye, if you will. So when we detect motion on our peripheral vision, we respond by looking in the direction of that motion. That's the corpora quadrigemina controls that. The superior colliculi directs us to a sudden movement, a bright light, any kind of visual impact. It also allows us to track objects that are moving, and whether we are driving in the car and trying to assess when we're going to pull out at an intersection, or how close, when do you apply your brakes, that kind of thing. Any kind of motion coming towards you, or like just watching a baseball game or a football game, and you can, if you'd like to watch baseball and you go out to the Smokies, and if you sit right behind home plate, every hit out in the center field is a home run until the center fielder catches it about 10 feet behind second base. But we still track it with our eyes. So inferior colliculus is sudden sounds. It's a startle reflex. We respond to noises. We jump when that happens. We turn our head in the direction of the sound. Those are the kind of things that the inferior colliculus does. Someone calls your name and you turn your head in the direction of the sound. And so so these two reflexes there are designed to protect us. Now let's move on. We're done with the midbrain. The corpora quadrigemina is on the dorsal surface of the midbrain. So that's that. The midbrain is that in the front is a structure shaped like a bird, if you imagine it. And then the dorsal surface is back here, and this green area is the corpora quadrigemina. Now the pons doesn't have a lot going for it as far as we're concerned. It's just a not really, but the pons is a crossover center for spinal tracts, spinal nerves coming up from the spinal cord. Because our brain is contralateral, meaning that the left side of the brain controls the right side of the body. So the nerves, the tracts that are coming up, are going to have to cross over somewhere, because nerves from the left side have to cross to the right brain, and nerves from the right side have to cross to the left brain, and they usually cross at the pons. So there are some breathing centers in the pons, but its primary role is to allow these nerves to go to the opposite side of the brain. Now the medulla, at the end of the brainstem, is it sort of runs into the spinal cord, and it's sort of problematic where the spinal cord begins and the medulla ends, but the medulla is very, very important. Now, it's a passageway for the tracts going down and the tracts coming up, but it also has a cardiac acceleratory center to speed up the heart when we need it to go faster, a cardiac inhibitory center to slow it down when we want to rest. It has two big nerves that control the speed, the force, and the rate of the heart rate. It does not have any control over the heart. The heart is a self-starter. It will beat on its own, but these cardiovascular centers, these acceleratory and inhibitory centers, simply speed up the heart or slow it down as we need. We also have a vascular center in here that controls the size of our blood vessels. We can open up vessels to increase blood flow. We can shrink blood vessels to reduce the flow. We also set our breathing rate in the medulla. The medulla controls our breathing rate. Our normal breathing rate is 15 times a minute every 4 seconds. We can pick up that pace or slow it down depending on what we're trying to do. We breathe faster after exercise to get rid of carbon dioxide that formed from the Krebs cycle. That's the only place in our bodies where carbon dioxide comes from, is the Krebs cycle. It makes our blood more acidic. That increased because the carbon dioxide combines with water in the plasma to form carbonic acid. That tells the medulla, we got to breathe faster to get rid of that extra CO2. Breathing fast has absolutely nothing to do with oxygen. I haven't said that enough this semester, but oxygen is not the driver for breathing fast. It's the presence of carbon dioxide. Something else that's important here in the medulla is the medulla controls our ability to swallow. The hypoglossal nerve, it goes down the hypoglossal canal next to the foramen magnum on each side of it. There's little tiny openings there. The hypoglossal nerve connects to the tongue and the mouth and controls our ability to swallow food and water, and to chew and to speak. And so that control for that swallowing is in the medulla. A patient that can't swallow, a patient that has trouble swallowing or chewing or eating after having trauma or complaining of dizziness and a pain in their head may have had damage in their medulla. So not always. Sometimes they just have a pain in their head and then something else occurs. But a lot of times, a person who's suffered a small stroke in the medulla, the only indication you get of that may be that they start choking on their food when they try and eat. Or even worse, the only indication that they may have had a small stroke is about 4 or 5 days later when the patient develops pneumonia because they've been aspirating food into their lungs. So it's a reflex center. Coughing, sneezing, swallowing. Once we make the conscious effort to swallow our food, it becomes automatic. It becomes a reflex at that point. So that is the medulla. That's the end of the brainstem. Now, the brainstem does have a big structure that runs all the way through it from the midbrain all the way down through the pons and through the medulla, called the reticular activating system. This is the reticular formation. It connects to all parts of the cerebral hemispheres. The reticular activating system is monitoring all sensory input all the time. Right now, we're in this classroom and we are receiving sensory input from everything around us: light, sound, odors, irritation from our clothing, from our shoes, contact with the seed. My voice may be too loud for you or too annoying. Can't do anything about that. But all these things are sending inputs into the central nervous system. Now, a lot of it we filter out. We don't pay attention to the noise of the heating and cooling system until I pointed it out to you. Now you hear it. You didn't hear it before. You don't hear the sound of the projector. Cameron may, but the old projector was a lot noisier. Do you hear it?
Not really. No.
Okay, the old one you could hear. Yeah, you hear it. Okay, so she hears it. Okay. I hope I haven't made you now for the next hour and a half sit and think about that.
Well, the air always bothers me.
Really? Okay, so you're sensitive to that. We're all paying, we are not generally paying attention to a lot of the background stimulus, like pressure on our seat if we're sitting there, or the pressure of the constant touching of our clothes on our skin. Like maybe you have a tag in your collar that you weren't thinking about till I just brought it up. Or thinking about, the cuffs on your shirt or the tightness of your shoes or anything like that. That all sort of goes into background thanks to the reticular activating system. If we didn't have that in place, we would get overwhelmed by all the sensory input that's bombarding us all the time. The background noises and sounds and odors and stuff like that. I mean, this is a real simple one. Think about somebody that lives near a busy highway. After a while, they stop hearing the road. If they were to live near, the interstate, and it was the constant noise, it would fade in the background. The only time they would notice something was when it got quiet. See, that's what the reticular activating system does. It keeps us from being overwhelmed by the background sounds, but allows the important stuff to come through. It maintains our level of consciousness. So we're here in class and I'm rambling on and you hear this, but you're not paying attention to outside noises. You may notice somebody walking up and down the hallway, whatever they're doing, or you may, we may get a storm today and you may, see it raining and like that might attract your attention, but then it goes away. You don't pay attention to it. The reticular activating system will only allow things that are important to come through. For example, at night, during the night, your heat goes off or your AC goes off. And if that happens, it gets very quiet. Well, your body is used to the sounds of the air conditioning system running during the night, the low background noise. I'm sure you may be aware of that. And as it cycles on and you hear the heat pump outside come on and go off and come on and go off. Even when we're asleep, our ears are still functioning. And so all these background sounds, as the heating and cooling system is in play. When it goes away, we notice it. The reticular activating system says, hey, it's too quiet now. You might want to check that out. And so you wake up because now the house is too quiet. Or a bright light wakes you up. Or a noise outside wakes you up. If you have a child and your child cries or coughs funny, you wake up for that. Parents will often say that if they're with a group of kids, like something at school, and their child coughs, they can detect it right away. They know the sound of their child coughing or sneezing or laughing. They can pick it out right away. And so we respond to extraneous signals that the reticular activating system lets in. Now, when we go to sleep at night, the system is still working. It shuts way down because we don't pay attention to a lot of background noises then. We don't pay attention to the pressure of our head on the pillow or the weight of the covers or anything like that when we fall asleep. But our ears are still working and our body temperature is still working and our reticular activating system is still monitoring what's going on. So at night, we wake up when a funny sound occurs that we're not used to. Some of us can sleep through thunderstorms and some can't. You may sleep through the noise of the thunder. You may sleep through the lightning, the flash that lights up the inside of the house. Unless it's hitting you, then you don't have to worry about it. And others are awake constantly because they jump when, when you have a loud crash of thunder, and other people sleep right through it. It's the reticular activating system. Now, during the day, it works for us to keep us awake and alert so that we pay attention. It helps to filter out all the extraneous sensory input that may not be important, because we don't really care about the pressure of our shirt on our skin right now, or are my shoes a little too tight, or are they very comfortable? We're not, unless we have to stop and think about it, we're not going to pay attention to it. We're going to pay attention to the things the reticular system lets in. So let me, come in here. Okay, just do the best you can. So let me, now, the reticular formation can be affected by medications and recreational pharmaceuticals and real pharmaceuticals and alcohol. It can be damped down itself where you don't pay attention to things, where like you can sleep through it, or you don't become aware of it. So, yes.
How does it know what to let in?
It probably from practice and experience. It knows what it blocks out are what it would consider to be the background. Anything unusual that your memory doesn't recognize, or because like when your ears are when you're asleep, your ears are still processing sounds, and so as long as the sounds that your memory says should be running along, you're fine. But if there's a different sound, like breaking glass or a loud noise, like an accident out in the street or something, or someone trying to break into your house, or your dog starts barking because there's somebody in the yard, or you smell smoke, you wake up because you smell smoke, not because your smoke alarm went off yet, but because you're picking up an odor that you weren't used to. Something that's different from what we've gotten used to is what it will trigger. It has to be a stimulus that is unusual than normal background. A lot of that's based on our memory because our houses tend to make the same noises all the time. If you really think about it, the air conditioning, the heat and air conditioning makes the same sounds all the time. Our dogs bark all the time, all the same way every time. If this had been AP1 last semester, you would have gotten to enjoy hearing them run into my office and bark at people outside, even when there wasn't anybody there. So, but that all falls into background, extraneous stuff that we filter out, because it's only when it becomes something unusual do we respond to it, or something that we've through our memory have been alerted to, like the sound of our child coughing or sneezing, or crying during the night. So even if you have dogs and cats, even if they're making a funny noise during the night too, so something different is what triggers the response. It's a good question, because everybody's background stimulus is going to be different. So, are you going to pay attention to air movement? Are you going to pay attention to odors? Are you going to pay attention to outside noises? It all depends. What are you used to hearing and smelling normally? Anything that can penetrate through the reticular system will trigger, cause you to become awake. Or during our daylight awake time, it will, allow in what we need to have to operate. It's not going to let in everything, because we would get overwhelmed, so, because there's a lot of sensory input that we're not processing right now. We're doing a lot of visual input, auditory, but a lot of tactile stuff is sort of pushed off to the side, which is good because we would pretty much get overwhelmed. So I hope you're just yawning because you're tired and not bored. So I'm not picking on you. So anyway, that's the reticular activating system. It's really important for us. Where we get in trouble is with if we artificially damp that down with pharmaceuticals and alcohol, or a combination of both, or trauma. And that then makes it more difficult to, sometimes it will affect the ability to even become conscious and stay alert. So, okay. Now the next area, right behind the brainstem, is the cerebellum. The cerebellum is the second largest portion of the brain. It is a motor refining area. Most of our muscle memory is stored in the cerebellum. When we practice activities like sports or driving a car, riding a bicycle, swimming, the more we do it, generally the better we get at it. Maybe, and what the cerebellum does is as we practice and practice and practice and get better and better at what we do, we retain the memory of how we did that, so that every time we do it, we get better at it. The more we, like if you've ever played an instrument, you practice and practice and practice, and you get better as playing a certain piece as you practice it. Or play sports. That's why you have practice when you play sports. You get better by doing the same things over and over and over again, because it's stored in your cerebellum. The other thing the cerebellum does for us is it regulates our posture, balance, and equilibrium. It uses the large skeletal muscles in our body, the postural muscles, like the large back muscles, the large leg muscles, the quads, the hamstrings, to hold us upright, to keep us in balance. We depend on input from our eyes and the proprioceptors. We have that writing reflex. It always tells us to find the horizon so we know which way is up. And we have something to compare to for our balance and equilibrium. And this is what the cerebellum is going to do. It's always going to try to keep us in maintain our posture, maintain our balance, keeping us pointed up, so at least we know which way is up, so we're straight. And it is sensitive, it's very sensitive to disruption. The semicircular canals. What is that?
I don't know, but it's bothering me.
I hear
When
it.
I hear it, it's like it feels like a screeching noise.
Oh, I bet they're drilling somewhere.
It's driving me. It's
Yeah.
driving
I think they're like putting in security cameras.
insane.
They're putting in new security cameras for us.
It's driving me
I'm sorry.
fixing on certain things. And it's just-
They must be going downstairs because there's nobody in the hall. So now I hear it too. Thank you so much. Anyway, the
My ADD is like going crazy right now.
her reticular activating system, you get extra points for that because it's working overtime. Now, I'll just talk louder. So the cerebellum is affected short term by disruptions in the semicircular canals. You go on a ride at Dollywood, it whips you upside down and around, like maybe the Eagle or whatever. I know there's other rides that are just as traumatic to the inner ear. That's the best word I can say, because you're throwing these semicircular canals around in positions that they're not expecting. Okay. And so you jostle all those hairs inside the semicircular canals, and you can't maintain your balance. And of course, the information that the cerebellum is getting about which muscles to contract and which ones not to you end up coming off of a ride like that. If you're particularly susceptible to rapid motion, you have a hard time maintaining your equilibrium. You get the same effect, it's a little more gently with alcohol. Alcohol inhibits certain muscles, certain parts of the cerebellum, as do various medications. You know, the ones that say, do not drive a car after taking this medication, you know, do not operate heavy equipment after using this medication type of stuff, because your cerebellum is going to be impacted by it. Now, any kind of activity in the brain is measurable. You know, the reticular activating system is monitoring external and internal stimulus. The cerebellum takes this. Essentially, what the cerebellum does is it takes signals that come from the cerebral hemispheres that say, hey, raise your right leg. Well, the cerebellum uses those action potentials and refines it and tells you how, or the best way to raise your right leg. You know, the cerebral hemisphere says, raise your right leg, and the cerebellum says, we're going to do it this way because it's the most efficient. All that is measurable activity, and we measure it with brain waves. Now, brain waves are nothing more than action potentials shooting across the brain. And they occur in different patterns, depending on age and mental health of your patient, as physical health of the brain. These brain waves are nothing more than depolarization waves moving across the brain, but they fall into 4 distinctive patterns. So it's just a whole series of action potentials. Instead of one action potential followed by another, these are millions of action potentials all running in the same type of pattern. And we measure it on an electroencephalogram, which is sort of like an electrocardiograph, only instead of having measuring action potentials going across the heart, we're measuring it across the brain. Now, there are 4 types of brain waves that we've identified. The alpha waves. This is the resting wave. This is the red one on the chart there. You notice that the peaks and valleys are pretty close together, but they're all about the same size. So this tells us that we are in a resting state. You know, while the peaks and valleys are close together in the same size, they are the bottom of each peak is pretty broad. If you see, at the bottom there, you can see that there are, they're not right, not crisp, straight up and down lines. That tells us our brain is awake, but it's in a resting state. You're relaxed. You're not worried about anything. You're not really thinking about anything. And so, while you are awake, you're just sort of, just not really doing anything. Beta waves are what you get when the brain's active, like you're driving a car. I used to say, or when you're paying attention to class, but driving a car is probably a better analogy. Mental activity. Look at the brain wave there. The beta wave, the blue wave, look how close together the peaks and valleys are. It shows that more and more action potentials are being fired from different parts of the brain, but they're also consistent. Again, the size of the action potential, the wave formed by all these action potentials is pretty consistent. Signs of, consistency is the sign of a healthy brain. Consistency is the sign of a healthy brain. We don't have a lot of irregularities. Like consistency in a heart rate is signs of a healthy heart. We don't want to see any arrhythmias going on in the heart. Theta waves, the third category, we see this in children all the time because children's brains are still developing and children's level of attention and awareness is all over the place. Children they learn by all the stimuli that they receive. for good or for bad. And so their brain waves, their action potentials going across the brain can run in very narrow peaks and valleys or very broad peaks and valleys. Still fairly consistent in size, but you have some pretty unique irregularities in there, like, oh, look, a red ball, or oh, look, a truck, or oh, look, a balloon, or something like that, because children's brains are still developing. The pathways that they're going to use and continue to use as they get older are forming now. I mean, the neurons are all there. Just which pathways are we going to use to do certain things? And so, we're developing those pathways. Now, an adult should not be showing theta waves, because an adult should have alpha waves or beta waves when they're awake, when they're alert. The brain should be processing information consistently with a consistent pattern all the time. The theta waves show that there is something unusual going on in the brain. If an adult brain is showing that, then something's going on. We don't know. We can't look into the brain and say, oh, look at that. The best we can do is look at these tracings and say, oh, that it shouldn't do that. Is there something going on? Now, the last wave is both perfectly normal and unusual. Delta waves, perfectly normal to see those when we're asleep. The reticular activating system has been damped down so that we are filtering out a lot of extraneous stimulus. The important stuff still gets through, but we're not getting any visual input. We're not getting any, we're blocking most of the tactile input. You get cold at night, so you pull the blanket up, or you get hot, you kick the blanket off. That's a little influence you might get. You're not gonna, the sounds are in the background. They're only gonna trigger something if you stop hearing them or if you hear a different sound. So our reticular activating system has got us nice and relaxed. And so we can see how the peaks and valleys are very far apart. We're not sending as many action potentials anymore. They're still pretty consistent though in their size. But if we have an adult that's awake and we're getting delta waves, then it means that it may mean that they have some sort of brain damage going on. Now, it won't tell us where yet. We can isolate that from other tests, but if there's something going on with the brain, then an adult that's awake would likely show delta waves too. Now, I don't want to keep going back to the reticular activating system, but that's what lets us sleep. We have sleep cycles and we have awake cycles. We go through this on a daily basis. We call it part of our biological clock, or what we call the circadian rhythm. We are generally awake during the day and asleep at night. In fact, our body starts to prepare for sleep once we lose the visual cues of daylight. And part of our awakeness, if you will, alertness, depends on receiving cues from our eyes saying, hey, it's light outside, I need to be awake, as opposed to when it's dark outside. We may start getting sleepy because of that, because of the biological processes that are allowing us to essentially shut down for the night. So sleep is a type of unconsciousness. It is not, like a coma or full blown, you've been injured and in an accident and you're unconscious from a blow to the head. This is something that you can be woken from, aroused from. Sleep falls into two general categories, what we call REM sleep, rapid eye movement sleep, and non-REM. You know, they were very clever when they named it, non-REM and REM. Apparently, when we sleep and when we dream, our eyeballs move underneath the eyelids, and you can see that. You can see the eyeball moving around underneath the lid, and we call that rapid eye movement, and that indicates dreaming. And we can measure that with an electroencephalograph and see changes in that to indicate that we are not just, you know, asleep, but our brain's active, doing something. REM sleep is important for us. REM sleep allows our subconscious part of our brain to rest. Without REM sleep, our brain doesn't rest. So we need to have that resting. You know, physical rest, you know, just sleeping without dreaming allows our body to recover, but we don't feel as good as we could if we don't dream. So sleep aids that only put you to sleep and don't allow dreaming ultimately don't really help you a lot. So, because you have to have the dreaming to renew the subconscious portion of our brain. So we start out and we go to sleep. When we fall asleep, we are in what's known as non-REM. And there are 4 stages of non-REM. Takes us about 45 minutes to get down to stage 4 of non-REM sleep. And then another 45 minutes or so, about an hour and a half after we fall asleep, we're finally moving into REM sleep and we start dreaming. We may only dream for about 5 minutes, and then we move back into non-REM. And we'll cycle like that all night long. But the longer, you know, the more we cycle, the longer we're going to stay in REM sleep. We can, as we go further and further through the night, we may stay in the dreaming stage for up to an hour. So this is what it looks like. You can see the eyelids moving, you can see the eyeballs moving around underneath the eyelids. Obviously, you know, because when we dream, we're seeing what we're dreaming about. So, and that's why they call it rapid eye motion. You know, the eyeballs moving around. Now, while we're dreaming, we're not paralyzed, but our muscles, our skeletal muscles, are generally inhibited from acting out our dreams. You know, if we're dreaming about falling or flying, we're not going to try and fall out of bed or fly or something like that. But we do have, many of us have very active dreams, and we inhibit our skeletal muscles from acting them out. So the dreaming takes place in REM sleep. Nightmares occur in non-REM 3 and 4, the later stages of non-REM. And we may slide from a dream into a nightmare as we're moving through a stage. Many of those kind of dreams, though, nightmares may occur and we don't remember them. It's challenging to try and remember any of our dreams. You know, we remember some dreams, but not all. Usually the last thing we dream about is what we might remember when we wake up. So, and a lot of times as we are moving up from REM into non-REM, as we're starting to wake up, something that is happening around us outside, you know, in our house, outside our house, may intrude and become part of the dream briefly, like sounds or, you know, other things like that. So dreaming is occurs in a measurable pattern. We tend to alternate between REM and non-REM, you know, during the night or during our sleep cycle. We get further and further into the REM state the more we cycle through here. Again, the longest lasts about almost an hour. Many of our dreams fall into the same patterns. We all have, at some point, you may dream that, well, this is a very common dream, is to be late for class or to not be able to find the classroom or it's the last day of the semester and you're showing up for the final exam and you forgot to come to class for the semester, and you're trying to pull it all off on that last day, except you can't find the classroom because the signs are missing or the building's locked or something like that. You know, those are referred to as stress dreams, you know, and for the obvious reason, you know. Other types of dreams are flying dreams are very common. Traveling dreams are very common. Being naked in public and nobody noticing is very common. You know, it just occurs, you know, so we all tend to fall into the same patterns of our dreaming. So, okay. So we've taken a look at the brainstem, we've taken a look at the cerebellum, we've seen the reticular activating system, we see how it affects our sleep. We looked at how reticular activating system filters out a lot of our sensory input. Now let's talk about the area that gets it first. That's the diencephalon. The diencephalon is the center of all, is the receiving center for all sensory input. All tactile, all odor, all light, all sound, everything, visceral and somatic. The diencephalon is at the top of the brainstem. It consists of the thalamus, that's that green structure, and the hypothalamus, that's the orange structure. The thalamus receives all sensory input except odors. Thalamus gets odors by way of the mammillary bodies, and the thalamus is also the structure that controls our autonomic nervous system. And it's the link essentially between the endocrine system and the nervous system. You're all about the endocrine system in AP2. So the diencephalon consists of the thalamus and the hypothalamus. It is surrounded by the third ventricle. It says surrounds, but it should be surrounded by the third ventricle. The third ventricle is one of the cavities in the brain filled with cerebrospinal fluid. Now these cavities are all connected. So the third ventricle is connected to the lateral ventricle and the fourth ventricle and the cerebral aqueduct and the central canal leading into the spinal cord. So, but for right now, we're just going to say it's surrounded by the third ventricle. So the thalamus is in the center of the brain, the top of the brain stem, and all sensory input from every sensory receptor has to go through there, except odors, and then get routed to the appropriate area in the brain for processing so that we know what it is we're being stimulated by. If you hear sounds, you have to know what they are. Well, the sensory receptors can't tell you, and the thalamus can't tell you, but at least the thalamus will route the action potentials to the temporal lobe where we process sound or vision. It will not tell you what you're seeing, but it will send the action potentials to the occipital lobe, the back of the brain, where we process vision. Now, the hypothalamus is going to monitor odors, and it's going to monitor a lot of reflex activities. It will deal, it's often called our body's thermostat. It regulates our body temperature. It also controls the pituitary gland. So here's our thalamus. It is two structures side by side. They're paired. They look like little eggs, and they're about 1 inch long each. So, you know, like a little tiny egg. It is a relay center, and you can see where it's located right there at essentially on top of the brainstem there. And thalamus has a lot to do with emotions. Has a lot to do with emotions. The thalamus is part of a structure called the limbic system. The limbic system is our emotional brain. And so we respond to things. Since all sensory inputs going into the thalamus, it's going to be where we get triggered for emotional responses. So, because our emotional brain is controlled by a structure known as the limbic system, and the emotional brain is always at war with the logical brain. The logical brain is in the front of the brain, and it's fighting with, you know, the logical brain and the limbic and the emotional brain are always trying to see who comes out on top. So there is our thalamus. The hypothalamus extends from the optic chiasma to the mammillary bodies. So that whole area in purple. It is our body's thermostat. It processes information on odors and smell and hearing and osmotic concentration. This is where if we get thirsty because our mouth is dry, you can thank the hypothalamus for monitoring the osmotic levels, the salt levels in our blood. It will allow us to deal with issues on from the skin and from the viscera, and it will connect and control the pituitary gland. The pituitary gland is a little thing in pink that hangs down from the purple hypothalamus. Pituitary gland is the master gland of our body. It releases 8 different hormones. It's found in the sella turcica of the skull. Sella turcica of the sphenoid bone is where the pituitary gland is located. And it is under the control of the hypothalamus. The hypothalamus will tell the pituitary gland which hormones to release and when. So that makes it the link between the central nervous system and the autonomic nervous system. The hypothalamus also regulates a lot of different emotional responses for us. You know, rage, anger, aggressive behavior or passive behavior are controlled more or less controlled through the hypothalamus. Our response to pain, our ability to deal with pain comes through the hypothalamus, as does pleasure. Sexual arousal comes through the hypothalamus. The need to eat, the need to drink is controlled through the hypothalamus. It also helps to control our sleep cycles. So it has a great influence in us in what we do. There's the pituitary gland. There's, oh, I should have make it back here. Come on, there we go. And there's our pituitary gland right there. So a person who deals with aggressive driving or is exposed to road rage or experience or becomes involved by showing road rage, for example, or aggressive behavior, the hypothalamus is driving all that. You know, sexual arousal is being driven by the hypothalamus. So, and the need to eat, the need to drink, the need to stop eating and stop drinking when you're satisfied comes through here too. Now, there's one other area in the diencephalon. There's two small areas here behind the thalamus itself. And we have what's known as the epithalamus. And that includes the pineal gland right here and what we call the habenular nuclei. Now, the pineal gland does a really important job. It releases the hormone melatonin. Melatonin is what allows us to sleep at night. Melatonin makes us sleepy. It regulates our biological clock. Based on the visual cues, our eyeballs are telling us if it's light outside, the pineal gland doesn't release a lot of melatonin, so we're not sleepy during the day. When we lose the visual cues, when it gets dark out, when the sun goes down, then the pineal gland starts releasing a lot more melatonin. which increases our sleepiness level and makes us fall asleep. This is why it's so hard to work shift work if you're constantly bouncing from first shift to third shift, or, and because as hard as it is to stay awake at night, it's just as hard to go to sleep during the day if you're getting this, the wrong visual cues. And if you don't think visual cues are important, consider what happens in your dementia patients. There's a condition known as sundowning, where your patient becomes more and more agitated. Your patient with various types of dementia will become more and more agitated as they're losing those visual cues as it gets dark. It's a known phenomenon that happens to many, I'll just say Alzheimer's patients, but that's just only one of many different types of dementias. So the habenular nuclei tells us how to respond to odors in an emotional way. Something that smells really disgusting, like a dead animal, we have a visceral, almost nauseated response. Something that smells, pleasant is, oh, it smells good. You like the odor of the flower or whatever. Or baking bread, or barbecue, cooking on the grill, or any kind of odor that we like. We often have a very positive emotional response. That also ties into memories too. And we find that memories and emotions and odors are really, really linked together. So the habenular nuclei can let you be pleased or disgusted or nauseated based on the odor that you detect. So there's the epithalamus. And this is, it's above the corpora quadrigemina, hangs down right between the occipital lobes of the brain. And we also have behind it, which doesn't show up here, is the habenular nuclei that allows us to deal with odors and certain levels of food and water, but primarily emotional responses to odors. Okay, so we've covered everything now except cerebral hemispheres, the largest portion of the brain. The cerebral hemisphere is the paired hemispheres that sit on either side of the brain. Looking at the brain model, this is a life-size model of the brain. I'll put this up here. Let's stay together. There we go. And help. Let's see what we got. There we go. There's our brain. These are the cerebral hemispheres here. This is life size, just to give you an idea. And you can see I can cup it in my hands like this. But these are the two hemispheres divided by the longitudinal fissure running down the middle. For perspective, just how big it is. This is a half section here. So we can see, this is the hemisphere here. So they're about the same size. This is about the size of a human brain, pretty close to life size. So now let's get back to. So the two cerebral hemispheres are divided by the longitudinal fissure. They are connected by a structure called the corpus callosum, which is a series of fibers that run from one hemisphere to the next. So that we use the corpus callosum allows the left side of the brain to talk to the right side, allows the right side to talk to the left side, so that they know what's going on. These cerebral hemispheres include the cortex, which is the most important region in the brain, the medullary body, and the basal ganglia. Basal ganglia, we mentioned that the other day. That's that area that is going to refine motor activity, but it's going to deal with competing and inhibiting signals. So affected. You know, it depends on dopamine to inhibit the antagonistic signals, and when the dopamine goes away, we end up with a patient with Parkinson's disease. Anyway, the cerebral hemisphere is the outer cortex is covered with gray matter. This is where we talk about the gray matter of the brain. The last 4 millimeters of the brain is the cortex. It is this area that we consider as the gray matter right along in here. So this area just on the edge is the gray matter. You know, it is literally the icing on the cake, if you will, because the cortex is where we are located. Everything about us, our personality, our memories, our emotions are all found in the cortex. So it is an extremely important region for us. So everything underneath it is white matter, and there may be some gray matter areas in there. So the gray matter is unmyelinated axons and cell bodies. The white matter is myelinated axons. In the cortex, it doesn't matter if it's unmyelinated because the distance that it's communicating with other neurons is so short that the speed is still instantaneous. The ridges on the brain are called the gyruses, and the grooves are called the sulcuses or sulci. We use those to increase the surface area, but there are some very prominent landmarks based on these grooves and ridges. If the sulcus is very deep, we call it a fissure. So we have the longitudinal fissure separating the two hemispheres. If the sulcus is very large, we call it like the central sulcus. We use it as a very distinctive landmark. In fact, we have the central gyrus and the central sulcus, which divides the frontal lobe and the parietal lobes apart. And that pretty much divides the area between motor activity and sensory input. So now let's move on. So here are the lobes and the fissures. We have the temporal lobe, frontal lobe, parietal lobe, and occipital lobe. The same name as the bones that lay on top of them. Whether we probably named the bones after we named the lobes, doesn't matter. Frontal lobe is a motor area. Motor activity starts in the frontal lobe. Our personality and our behavior, our emotions, our memory are all going to arise from the frontal lobe. Our sense of right and wrong, our sense of fairness, our sense of justice are all found in the frontal lobe. Right behind the frontal lobe is the parietal lobe, or the parietal lobes, I should say. That's where all of our sensory input starts feeding in. From skin and from muscle, we process all of our sensory input there so that we know what's happening to us. Behind that, behind the parietal lobe, we have the occipital lobe. This is our visual area. It's about as far from the eyeballs as you can get, but this is where we process vision. Excuse me. And on the sides and the temporal lobes, we have hearing, smell, and taste. So fairly close to where the sensory receptors are. The occipital area, however, doesn't share with anybody. The occipital area is the largest, what we call association area and cortex. We call it the visual cortex of any portion of the brain, because we use vision for everything. So, major landmark in the brain is known as the central sulcus. The central sulcus divides the frontal lobe from the parietal lobe, and the central sulcus would be located, let me show you on our little model here. The central sulcus is located right about this area here, where we separate the frontal lobe from the parietal lobe back here. The central sulcus is a very large groove. The illustration may look even better. So there's a groove right here called the central sulcus. In front of the sulcus is what's known as the precentral gyrus. It's the ridge outlined in blue. It is that large gyrus in front of the sulcus. That's the central sulcus, so we call it the precentral or the in front of gyrus. And since we have a precentral, we got to have a postcentral. And that's the ridge of tissue behind the groove. But the central sulcus is the demarcation line showing between motor activity and sensory activity. Everything in front of the sulcus going forward is all motor. Everything behind the sulcus going backwards is all sensory. Now there is one more sulcus here called the lateral sulcus, and it's somewhere, it doesn't show up well, but somewhere down inside here, you'll see it in the next picture. There is one more lobe embedded at the lateral sulcus. It's called the insula. This is the insula down in here. Here's the central sulcus right here. There's the postcentral gyrus and the precentral gyrus. There's the parietal lobe, the occipital lobe, cerebellum. This is part of the temporal lobe has been removed to show you where the insula is located in here. Okay, so that is the fifth lobe. We'll get to what it does here in a minute. Now in the cortex, we have three areas of processing. Now remember, the cortex is just that outer 4 millimeters of the cerebral hemispheres. It has motor areas in it. This is where all of our motor areas come from for voluntary motor control. We say, I'm going to raise my right arm. So I raise my right arm. I want to put it back down now. That comes out of the cerebral cortex in the motor area. And that's going to be in the front, in the frontal lobe. The sensory input is in the parietal lobes, but again, it's in the cortex. It allows us to recognize stimulus. The third area, the most important area, is association. That integrates all the information. The association areas of the cortex allow us to know what we're seeing, hearing, smelling, tasting, because we have to pull in information from all over the brain and process it so we know what a rose smells like, or what a red light means, or what a pizza should taste like. You know, when you bite into a pepperoni pizza, you expect to have the same flavor all the time. You don't expect it to taste like peanut butter. You expect it to taste like pepperoni. When you get something at McDonald's, a quarter pounder here should taste just like a quarter pounder in Omaha, Nebraska. They should always taste the same every time. You know, we expect our food to taste, you know, we already have our preconceived, you know, our preformed memories based on past experience of how food should taste, how odor should smell, how our, you know, we know when our shoes fit and our clothing fits. We expect, you know, if you're buying a size 10 or 9 or 8 or 11 size shoe, that it's going to fit because that's how big your feet are. Integration takes all of the information stored in our brain and puts it together and allows us to know what's going on. And 99% of what the brain does is association and integration. It uses multipolar neurons for this. 99% of all the neurons in our brain are multipolar, and 99% of those multipolar neurons are in the association area. So we don't give a whole lot of extra neurons to the motor and sensory because we don't need them. We get the signals, we do things, but what's more important is that we're processing this information. So we have this functional areas of the cortex. Association outweighs everything, tremendously. Now within the white matter of the cerebral hemisphere, so remember the cortex is just the gray matter. We have a lot of white matter underneath all that in the cerebral hemisphere. Because remember, we're only using this little bit here where the gray matter is located, right along the edge. Everything else underneath it is the white matter. And we use that to draw from. So now what do we do with that white matter? Well, we have fibers, communicating fibers that tell us so that we can collect information and bring it to the association areas, and that can tell us what is happening. 3 different types of fibers. We have what are called the association fibers that run up and down in the same hemisphere, front to back, back to front, on the left side and on the right side. We have the commissural fibers that go from left to right and right to left. The corpus callosum are the commissural fibers. And we have the projection fibers coming up and going down the spinal tracts, spinal cord, so that we get sensory input on the sensory nerves, and we have motor output going out on the motor nerves telling us to do something, or you are aware of something, or you're thirsty and you get a glass of water and you drink that. And it looks something like this. The commissural fibers are in green. That's the corpus callosum communicating left to right, right to left. So the left hemisphere knows exactly what the right hemisphere is doing. The projection fibers come up the spinal cord. Those are the ones in purple. So we communicate up and down from the spinal tracts so that we send motor signals out and we receive sensory input. The corpus callosum communicates side to side. And we have the association fibers that communicate front to back on each hemisphere. Something like this. And this is all in the white matter. And all this information is coming into the association areas in the gray matter in the cortex. And this is sort of exaggerated here because the cortex isn't quite as big as it shows here on the outer edge. It's really only about 4 millimeters thick. So it's not very big, but it does a tremendous amount of work for us. Now, to throw a wrench into all this, we have our emotional brain. You would think with our brain busy processing sensory input and figuring out the right answer to do things, we would just be, we'd always come along and do the right thing all the time. But we don't. The limbic system is our emotional brain. It includes the thalamus, the hypothalamus, the hippocampus. The hippocampus is the location that allows us to store memories. It doesn't make memories. We don't make memories, no matter what we hear in advertising. Memories are just the record of things that are happening to us at any point in time. That's all it is. I'm going to go make memories in my vacation. Well, yeah, of course you are, because you got your eyes open. The hippocampus is the area of the limbic system that allows us to store memories. The amygdala is a portion of the limbic system. It's a little green structure there. The hippocampus is the magenta colored structure on that round, that round blue thing, we call this limbic because of its shape, and it's sort of a circular pattern here. And the hypothalamus is right in front of the amygdala, and the amygdala is right below the thalamus. And we have the basal ganglia wrapped around there, so it controls our muscles. And we have we don't see it here, but there's a cingulate gyrus, which sits above the limbic system here. The amygdala is where we locate our fear response, where we learn how to respond to a scary situation. The cingulate gyrus allows us to respond to frustrations and to aggression. So these are two key areas here in the limbic system. Most of us have experienced both of those at different times. The limbic system allows our emotional life and our emotional response based on the memories of previous experience. You know, because everything we do depends on memories. You're driving down the road and the light turns yellow. What do? Well, you have memories of I can make it through, or I can't make it through. And that dictates what you're going to do. Are you going to step on the gas and try and get through, or are you going to slow down and stop? Particularly if there's somebody in front of you that already stopped. So we base our emotional response to things on our memories. Someone we love to see, someone we love to be around, we enjoy their presence, we have good memories of that. Other people that we cannot, that don't thrill us with happy feelings, you know, we don't like them, we don't like to be around them. That's how we respond. So the amygdala is our emergency response center in our brain. It teaches us what to do when we are threatened. It is the fear response. We learn how to act in a fearful situation. It triggers the fight or flight response. It tells us how to deal with emotional events and emergencies. You know, people that are well trained firefighters, police officers, rescue squad, paramedics, doctors, nurses, anybody in healthcare is trained on how to respond in an emergency situation. Many people do very well in emergencies, others don't. Not because of a character flaw, but because they just can't process it. So fear is used to trigger the amygdala and bring up the memories of how do you react? You know, what do you do in a fearful situation? And so it is, you know, the response to save you from, you know, a threatening environment. You know, the fire alarm goes off and we smell smoke and we see bright flames at the other end of the building. What do? Well, obviously we can leave the building. And yet there are people that would panic. Not anybody here, but there are people that would panic and run around and do. People have been known to do very bizarre things in a situation like that, you know, because they can't connect the fear response with the correct behavior. You know, children. What do children do in a fire? They often hide from it. They're found in a closet or under their bed, hiding from the fire. You know, a lot of times they don't survive that. So now, the amygdala also has a big role in how we feel about good things, pleasurable things. We enjoy, you know, a good meal. We enjoy a good movie. We enjoy music. We enjoy, you know, a nice day. Some people like cloudy days. I don't know. We enjoy things like that. Sexual arousal is driven by the amygdala. The amygdala may increase, actually physically increase in size depending on the age of the individual, their maturity level, and their sexual activity levels. So there's a lot going on here with the amygdala, not just in fear, but as well in pleasure and sex too. So which is very linked together. Now that's the amygdala. Now the cingulate gyrus, come on, here we go. Cingulate gyrus is directly above the limbic system. The limbic system is highlighted here in orange. The cingulate gyrus is right above it. The cingulate gyrus allows us to respond emotionally to different types of stimulus, particularly odors. Odors and memories and emotional responses are all linked. You may detect an odor of baking bread or baking biscuits, and that may say, that smells like grandma's biscuits. And your emotional response is, I really miss my grandma. Out of the blue, you smell these biscuits. You're walking down by the baking kitchen and you smell biscuits baking there, and it reminds you of grandma and you miss your grandma. Or your emotional response is, I hated my grandma. She made the worst biscuits. They were hockey pucks. And she made us eat them. That's an emotional response. The cingulate, it works both ways. The cingulate gyrus allows us to tie in memories to emotions based on odors. Pain. Many people don't like to go to the dentist because they have memories of pain and their emotion is fear. So they don't go to the dentist because they don't like it. They don't want to be hurt, and it's hard to get someone to think otherwise because there is a certain level of pain usually involved with going to the dentist. The other thing that the cingulate gyrus does, besides tying all this in, is allow you to deal with frustrations. If you've ever been, we get back into that third pathway for processing the fourth pathway, the one that allows you to have the aha moment, the post-discharge pathway, that you have different neurons running in different locations, and suddenly they all come together, and you said, that's how it goes together. The cingulate gyrus is pushing a lot of that for you so that you know how to get something done. But if you can't get it done, then you're frustrated. This is where people start throwing things and yelling at people, in a work environment, and are very frustrated. They may even indulge in behavior that is inappropriate by flipping them off. When someone flips you off, or as I like to say, well, they waved at you, but they didn't use all their fingers, or they forgot to. It's because their cingulate gyrus says they are so frustrated or so angry, that's all they can think of. So it is their cingulate gyrus speaking to you. Now, our response is going to dictate what happens in that situation. And does it get worse, or does it back off? So we've all experienced that. We've all had people, we've probably all done that to other cars that have cut us off or something. You've never done it, so.
I've thought about it.
Okay, there we go. You've thought about it, so you haven't done it. Well, at least we've thought about it. My wife won't let me do it anymore. So, or we've seen other people do it to us, So, and that's because they're frustrated, and they have the rage and aggression, and the cingulate gyrus cuts loose, and there they go. And if that's the worst that they're going to do, then you consider yourselves lucky. So, okay, and that's where we'll stop now. We'll wrap this up on Tuesday. And there's no lab next week or the week after. So anybody have any questions before I cut us off? Okay, then I'll see you all next week. Have a good weekend.